So welcome to the third lecture of module 6. So in the last lecture I have discussed about two modes of capacitive transducers. That is, one was by varying the overlapping area where we used it as a displacement transducer or to measure displacement or to quantify displacement. The second type of transducer, capacitive transducer that we discussed was by the variation of the distance between the two plates. So that mode of transducer, capacitive transducer, we used for measuring pressure. So pressure transducers usually work using the variation of small d. And today we'll see the third mode of capacitive transducers, that is by varying the dielectric constant. Now you can see a figure where this mode is usually used to measure the liquid level or to know the liquid level, or quantify the liquid level. So here we have a tank, and in that tank we have a non-conducting liquid. That is very important, a non-conducting liquid at the height of h1, and then above that we are having a height of vapor column above the liquid, that is h2. Vapor in general, it can be air also. So vapor column of height h2. So the total height is h1 plus h2. And in that tank we have two concentric cylinders. One, the outer concentric cylinder is having an inner radius of R2, and the inner concentric cylinder is having an inner radius of R1. So obviously you can see that from the figure, you can see that R1 is the inner radius of the inner cylinder, R2 is the outer radius of the outer cylinder. So R2 minus R1 is nothing but the distance between the two cylinders, or the separation between the two cylinders, that is A. And we assume that R1 is equal to R, so that R1 plus, that is 2R, that is R1 is equal to R, that is this whole diameter of the cylinder, inner concentric cylinder, is taken as 2R. Okay, so this is the figure, and there is a small hole inside the outer cylinder where the non-conducting liquid is allowed to flow. I mention it as a small hole because small hole will not allow perturbations in, or the perturbations or disturbance in the level of the fluid or the non-conducting fluid to affect inside or to get inside. That is, if the hole is small, that will not allow the variations in level of the non-conducting fluid to get affected inside the tank. So that is why we keep the hole small. But the hole is required because we need the non-conducting fluid separation between the two conducting concentric cylinders. I hope the figure is clear. Now we will move on to the explanation. Now this is the equation. Just know about this equation, that is the capacitor. So here we use the variation in dielectric strength. So based on the level of the fluid, H1 will change or H2 will change. Okay, so based on the liquid level, H1 and H2 will change. Now based on that, so now H1 and H2 are simply numbers. So you can see that this number is being multiplied with epsilon 1. What is epsilon 1? That is relative permittivity of the liquid or the non-conducting fluid. What is epsilon 2? Relative permittivity of the vapor above liquid. Okay, so and epsilon naught is, we know that is its permittivity of the free space. So this H1, which is a number, is being multiplied by epsilon 1. That means this number can increase or decrease. So based on increase or decrease of H1, this epsilon 1 is magnified or attenuated, or the value, this whole value depends on the magnitude of H1. Likewise, the whole magnitude of epsilon 2, H2, depends on the value of H2. So based on H2 value, epsilon 2 can increase, or epsilon 2 product can increase or decrease. So H1 will in turn affect this product, or in turn affect the dielectric value, but H2 will in turn affect this product or the dielectric constant. Okay, so based on H1, variation H1 and H2, dielectric values vary, as such capacitor value also vary. Now you can see that we have made certain things that define certain things, that like R2, what is R2, what is R1, what is A, and everything. So with respect to the height of the tank, R2 is very small. R2, as we know, it is R2 minus R1, which is very much greater than A, that separation to the two cylinders. I already told that R1 is equal to R, and R2 is equal to R plus A. If you substitute that, this is the case. That is C is equal to 2 pi epsilon naught epsilon 1 H1 plus epsilon 2 H2 by log to the base E 1 plus A by R. So the main conclusion is that depending upon the variation of liquid level, dielectric value, the product will change and capacitor also will vary. So how can you quantify the level difference? That is, if you plot a graph taking either H1 or H2 on the x-axis and on the y-axis if we have a capacitance, then with variation of either H1 or H2, we can plot a graph. So if we have a capacitance value, then you can extrapolate it to some H1 or H2. From that, we can get the value for H1 and H2, that is the liquid level. I think from the graph, it's the predefined graph. We have to plot the graph by doing some experiments, so that for varying H1 and H2, we get the values for different capacitance. So on the x-axis, take either H1 or H2, and on the y-axis, the resultant capacitance value. So this will be the graph which will act as a reference. So based on the value of capacitance we get when we do the test, this capacitance value will correspond to some value of H1 and H2, which defines the height. So from the value of capacitance, we can actually find the liquid level. So this is what is all about the third mode of capacitive transducers, that is using the variation of dielectric constant. So one requirement here it is that the liquid used should be essentially a non-conducting one. Why it should be a non-conducting one? Because the conducting plate should definitely be separated by a dielectric medium. So the quality of the liquid should be of a dielectric material. Okay, so that is all about this capacitive transducers. Now we move on to the next mode, that is we will move to the flow transducers. So here we learn about two modes of flow transducers. One is ultrasonic flow transducers and electromagnetic flow transducers, which are given in your syllabus. Now first we'll see what is an ultrasonic flow meter. So here we have two sets of transmitter and receivers. So one set will essentially have a transmitter and its own receiver. Both are piezoelectric crystals. So this transmitter A and this receiver A are made of same piezoelectric materials. So this likewise transmitter B and likewise transmitter B, receiver B. So in the transmitter A we have an oscillator. So a crystal oscillator. Crystal oscillators are famous for generating very high frequencies. So what is ultrasonics? Any frequency above the audible range is called ultrasonics. So you can take a frequency above 20 kilohertz. So this oscillator will generate frequencies above 20 kilohertz. So it's not normally the range of frequencies generated by crystal oscillators or this ultrasonics is varying from 0.2 megahertz to 5 megahertz. So this will generate any frequency between 0.2 megahertz and 5 megahertz, and this will generate ultrasonics. So these transmitters and receivers are digged in the wall of the pipe at some angle theta. Now, when they transmit these ultrasonics or the mechanical waves, ultrasonics are ultimately mechanical waves, they will pass through the fluid and received by the receiver, which is another piezoelectric crystal. So what happens? So these are mechanical vibrations or waves which will cause its own electrical signals. So based on that, so what is actually the principle? The principle is this one, that is the particles suspended in the fluid impart a frequency shift that is mainly due to the Doppler effect. The particles suspended in the fluid impart a frequency shift proportional to the particle velocity, which can be measured with a suitable electronic counter. So as I mentioned, so this frequency shift is imparted by the suspended particles, which is directly proportional, which has velocity of the fluid. Now, when the waves are passing through the liquid, these waves will be shifted by some frequency. So that shifted frequency waves will be received by the receiver A as well as the receiver B. So we'll see what are those frequencies. So the frequency received by the receiver of A is actually FA, which is equal to C plus V cos theta by L. How does this formula arrive? That is, we know that 1 by F is T. Time is nothing but distance by velocity. Now, so F is equal to velocity by distance. So this is the component which gives the frequency shift. That is, C is nothing but the speed of the mechanical wave, and V cos theta. What is V cos theta? That is, if I consider transmitter A and receiver A, this is angle theta. This is producing mechanical waves with velocity C, and this is the velocity of the fluid moving. So the component of the velocity of the fluid along the direction of the mechanical waves is nothing but V cos theta. That is, the component of velocity of the waveforms along the direction of mechanical waveforms is V cos theta. So we can see that this for transmitter A and B, for the waveforms generated from transmitter A or emitted from transmitter A, it is just like moving downstream. That is, the velocity increases by a component V cos theta. Okay. Whereas, take the case of transmitter and receiver B, where velocity decreases. It is just like moving upstream. That is, see, we are moving against the waveforms. The mechanical waveforms are moving against the velocity of the fluid. So obviously the velocity decreases by a factor V cos theta. Now, if we find, so these are the shifted frequencies received by the corresponding receivers. Now, if we find the difference in frequency, that is FA minus FB, we can see that 2V cos theta by L. Here, one important conclusion is that the difference in frequency is independent of the velocity of the mechanical waves. So, thing is that using some electronic counters, so here we get some electronic signals, electronic waveforms. Here also we get electronic waveforms. We can detect the peaks of these electronic waveforms by using an electronic counter. So these electrical signals will have peaks. We can count the peaks using an electronic counter for both receiver A and B, so that we get the FA and FB. Taking the difference, we'll get it as 2V cos theta. Knowing FA minus FB as well as theta and L. What is L? L is nothing but the distance of separation between the two, that is separation between the transmitter and receiver. Knowing the value, you can surely find the velocity of the fluid. Okay. Now we'll move on to the next one, that is the electromagnetic type of flow meter, where it uses the principle of dynamically induced EMF. What is dynamically induced EMF? We have a conductor moving inside a uniform magnetic field. What is statically induced EMF? That is, there the flux is moving, conductor is constant. Here the flux is constant, but the conductor is moving. Here we have the conductor as a conducting fluid. So the equation we all know, that is, it has E is equal to B dV into 10 raised to minus 8V. This 10 raised to minus 8V is particular to or pertaining to this method because the voltage is in the range of 10 raised to minus 8. That is, the generator voltage is very small. So we have a fluid flowing through a pipe wherein we have a perpendicular magnetic field. It's a constant uniform magnetic field. So when it passes, it cuts the magnetic field. So EMF will be induced across these two electrodes. So these two electrodes are kept on the bolts of the pipe so that the fluid can touch the electrodes. So the EMF will be induced across the electrodes, which is actually perpendicular to both the fluid flow as well as the magnetic field. So this induced EMF will be depending on the magnetic field B and the distance of separation between the two electrodes D and the velocity of the fluid. So getting the value of E, we know what is the B here. We know what is the distance of separation between these two plates. We can get the value for velocity of fluid. Thank you so much.